Welcome to the talk. The title is Autonomous Programming for General Purposes, Theory and Experiments. The outline: introduction. GENISAMA has 8 properties. APFGP stands for Autonomous Programming for General Purposes. I will talk about experiments, discussions, and conclusions. Introduction, we include Symbolic Schools, Connectionist Schools, and APFGP. Natural intelligence start from early philosophers like Plato and Aristotle. Artificial intelligence didn't start till Alan Turing, 1950s. There is a fragmentation within each discipline and also between 2 disciplines. The symbolic schools, by definition, start with handcrafted symbols and that are static and task-specific. Each symbol represents an atomic token that represent concepts like tasks, goals, purposes, contexts, roles, or features. Symbolic school systems are brittle because if the concepts that are required have not been modeled well, that system will break. An example of symbolic school, a well-known example, is a letter E with slightly different shapes defined by symbolic concepts like ages and interconnections. The connectionist schools are motivated by neural-like computations. Many neural networks, however, are also symbolic because each line corresponds to a symbolic concept. Typically, neural networks lack logic, and many people call it black box. Many claim that neural networks are less brittle, but I'm afraid not really, and I alleged frauds in Turing Award 2018. An example of a connectionist school is a neocognition by Fukushima. The limitation of connectionist schools include open skull, human intervention into the neural networks by changing its parameters or architectures or select features to detect based on human visual examination of the features and solutions. There's a new concept called post-selections. They use test set like a training set, only report the best network among many that achieved best score from the test set. APFGP could be a new school. Right now, it's still very early. Interestingly, all natural intelligence uses APFGP. It uses lifelong experience from zygote to embryos, fetus, newborn, infancy, and through adulthood. We like to ask, what is the minimal set of APFGP? Next, I'd like to discuss GENISAMA. It includes Agent FA, Attentive FA, GENISAMA Turing machines. Turing machine is a well-known model where you're giving a task, human design a machine with the known task. It has tapes, then there's a read-write head. Control is handcrafted by a human programmer. The control can be written as a mapping, start from current state, and the tape symbol read goes to new state, the new tape symbol to be written on the tape, and the head will move to right, left, or stationary. Universal Turing machines are still the same as regular Turing machine, except that the meanings of the input on the tape is different and the controls are different. Input tape has 2 types of material. One is program, another data. The controller emulates the instruction on the program. So it's a general purpose because a programmer can give any program as long as it's written in the language for universal Turing machine. An agent FA, by definition, is a finite state machine. It's also called finite automaton. We define a new kind of FA. It's agent FA. It just outputs states. The current state is output. And the states can be everything. Anything that you design the FA for. It could be actions, could be tasks, contests. And we define a new kind of FA called Attentive Agent FA. For example, in this case, you need to attend to the speakers, to other speakers, lips, and the nose, and so on. The Theorem 1 says that the control of a Turing machine is not only an agent FA, but also an attentive agent FA. because Turing machine attempts using read-write head. Then move on to GENISAMA Turing machine. What do you mean by GENISAMA? G for grounded, grounded in the physical world. E means emergent representations. Only emergent representations are allowed, no symbols at all. N for natural representation from sensors and effectors. I for incremental computation and not a batch computation. You cannot collect the data and you process the data. As for schod closed, you cannot open the network to change its parameters. Once the system is born, the schod is closed. A for attentive and for motivated, like pain avoidance and pleasure seeking. Emotion is a special case of motivation. A for abstract, so not just fitting data as a neural network can do, but must abstract from data to abstract rules. Let's look at the control of a GENISAMA Turing machine. Want to use the DN, developmental network, as the control. And we already said that the control of a Turing machine is FA. DN can learn any FA. So FA had a transition. Current state and current input move to next state. But we cannot use symbols, we use vectors. Z is a vector for Qi, X for vector for sigma input, and Z is for the next state for Q. And for the symbol, it's a monolithic, there's no structure. Vectors, you can talk about inside, we have pixels, we have multiple objects, you have variations, you attend to different parts of the vectors and the states. From symbols search to neuron computation. When we do lookup table, we just search for symbol match. Each symbol could be matched perfectly or different. But now we have vectors. We have Z for Q, X for sigma. We have a top-down input for matching Z. T for Z may not be exactly the same. Two symbols are either the same or different, and they are different, and they are different. So you want to search for all the T's, for Z, for all the B, for bottom-up weight, for X. Then the match is based on inner product. Use a dot, unified, unified, unified. So you have two parts. Top-down match between the top-down input with its top-down weights, and the bottom-up input X with the bottom-up weights. And that's typical for vector match. For symbol, it's very simple, just match or different. For vectors, we have to use weights, top-down weights, and bottom-up weights to match input from top-down and bottom-up. And the weight match is that among the neurons, say IJ neurons, and in Y internal representations, you find all the weights, IJs, that are matched the best, and the winner, in this case, only one winner. The representation of the match is represented by inner product. After we have a GENISAMA Turing machine, we can do APFGP. What do we mean autonomous programming? Consider two learning modes. Mode one, learning from a teacher Turing machine. It's a supervised. It's a simpler, but after we have a mode one understood, we can move on to mode two, where learning from real physical world without any accepted teachers. For example, we can do research. We can observe from physical world and we synthesize rules and verify those rules are correct or not. But mode one is a lot easier to understand. But after we learn a lot of cases, then we can generalize to learn directly from physical real world. Theorem 2 said, by learning from any teacher Turing machine, regular or universal through patterns with top-down filing in Y, the DN control enables the learner, GENISAMA Turing machine to emerge inside it with the following properties. If you have sufficient neuron, it's error-free. Insufficient neuron, it's optimal in the maximum likelihood. Theorem 3 says a GENISAMA Turing machine inside DN automatically programs for general purposes for a number of purposes after it has learned a universal Turing machine and the related purposes. The DM program itself is task independent and language independent. Let's take example, suppose we have a finite state machine or FA, and you have a state and you have inputs, and those are symbols. And in order to make emergent, we can use symbols, but rather we use vectors. Here we have muscles, we have pixels, and those are the muscles. DN can do APFGP. and very much like state transitions of time 0, 1, 2, 3, and those are the states in vectors, and those are the bottom up as vectors, including partial views, and neurons. In this case, 6 neurons have a bottom up weights, top down weights, and the winner will fire, and heap learning allow the linking to establish automatically. Symbolic networks, including many neural networks, basically has symbols, alpha, beta, gamma as a state, and AB as an input, and transition is in symbolic. DN grows a brain, a kind of coarse model of a brain, and each neuron has 6 fields, and a network starting from sensors. You have position motors, you have type motors, and it grows ventral pathways and dorsal pathways. How does DN segment? So even we have attention window, you still have background. And this is the true contour of the object that's learned. Contour DN will use synaptic maintenance to cut off the connection that has bad matches and keep the neurons inputs that has good matches. DN also need to handle invariance. In this case, the location at different locations, scale, big, medium, small, within angle, lighting, and multiple objects. You have multiple objects in the background, a hand and toys in background. Those are background. And attention will do that together. How the DN learn relationships? If you have one object, two objects, they can also learn a pair. For example, AB group, A plays B, A gives B to C, like that. Once you have motors, and as the input, then this is the relationship, then the neurons start to learn the relationship like logic. Let's talk about experiments. We talk about vision, audition, natural language understanding. In this case, for vision, you have input the cameras, then you have GPS input, camera local views, and you have automatic integration and learn from skills. Problem look very complex. You have Z, have many different concept zones. Then we input with local view and global views. But very simple for a child because everything inside the brain is automatic, and also simple for the brain modeled by DN, everything's automatic. And with a large data set, blue areas are learned, and dark red is test route. It's regular, but the bright red is blindfolded testing. But they are all successful. It handles a lot of variations like shadows, road edges mixed with shadow edge, and so on, including obstacles. Next audition, we learn a sequence of phonians and sparse labels, like this is the type of phonians. And the old method, we have k-means clustering to generate dense labels as a context. The new work to be submitted, there's no labels. You develop a model that provide continuous vectors as labels. We also learned the natural languages. We have a mother tongue, has English, French, bilingual environments without noise and has 0% errors. But if we have noise added, we have about 0.02% errors. So let's discuss. We solved the linear problems and local minima problems. It also no iterations. It's optimal in the sense of maximum likelihood and one single network only. We do not try many networks and report only one. Use DN tool, we have wide-to-wide connection, will think better and generalize better, but we will not be able to discuss this issue for the lack of time. Conclusions, APFGP has been proved using a constructive method. GENISAMA universal tuning machine by DN is general purpose. It's also fully automatic. This is the first time the learning is fully automatic inside the skull. We present experiments for 3 bottleneck problems in AI. Natural intelligence and artificial intelligence have been unified by the APFGP theory here. And the latest, we talk about consciousness in the machines. You're welcome to take a look. Thank you very much.